Well, here's part 2 of the screencast for week number 10. The subject is geometrical optics and optical instruments. It's 2 chapters in the textbook. So part 1 was on the theory and the equations for reflection and refraction. And part 2 will be on applications. We'll consider 2 cases: mirrors and lenses. So we'll start with mirrors. A mirror is a piece of glass with a silver backing. The silver reflects light. The glass is not important. And we have reflection at equal angles. So the reflection from a mirror is governed by the law of equal angles. And our first example will be a plane mirror. So in other words, we have a mirror and we have some kind of an object. Maybe it's a bowl of flowers. And you're standing someplace, maybe you're standing back here and you're looking at the reflection of the object, this bowl of flowers, in the mirror. So you can see light from you may be able to see light from the object directly, and you may be able to see light that reflected off the mirror. So you would see the object, and you would also see an image. You'd see a bowl of flowers over here. Of course, there is no bowl of flowers over here. It's just that it looks like there is, because that's the image. So we have the object, and we have the image, and we have light waves. Now, as you know, a light wave consists of, well, if we treat it as a plane wave, planes, which contain the electric and magnetic fields, and then a direction of propagation. So these planes perpendicular to the direction of propagation are called the fronts. And we won't be too much concerned with those. The direction of propagation, or the propagation vector, we call that the ray. And we'll be concerned mainly with the ray, because what we're studying here is the direction of motion of the incident light and the reflected light. And so for that direction of motion, all we need is their rays. And so the way we analyze reflection in a mirror is called ray tracing. So we'll represent the object as a source of light waves. These could either be produced by the object itself, for example, in a lamp, or more commonly, it could be reflected light, such as sunlight or light from a lamp, which comes off the object, and we want to trace that light coming from the object. We'll represent the object as an arrow. So here's our analysis of the image for a plane mirror. Let's see if I can blow this up a little bit. So here's the object. And here are 3 light waves, I should really say 3 rays, coming from the tip of the object. And the mirror is here. It's attached to some kind of a wall. So there's a wall here, and the mirror is mounted on the wall. So a light wave coming from the tip of the arrow reflects off the mirror and follows the law of equal angles. So here's another light ray that reflects off of the center of the mirror. This light ray reflects off the very top of the mirror. This light ray reflects off the very bottom of the mirror. Now you're back here observing the light coming into your eye. Well, this will come into your eye, that will not come into your eye. So actually, I have to think of your eye as being more like a camera, and your camera film is back here. And there's light coming into the film here, and here, and here, if the film stretches that far. The light seems to be coming from an arrow behind the wall. You know, if you had an arrow behind the wall, light from the tip would go down here. Light from the tip would go down here. Light from the tip would go up here. And you would get the same light arriving as you get light arriving from the reflected light in the mirror. So the image is an equivalent source of light, in this case behind the mirror, producing the same rays of light, ignoring the mirror, as you would actually have coming from the mirror. So what you see in the camera film is this arrow. That's called the image. So that's a simple example of ray tracing. It's simple because the reflections are just at equal angles and it's a plane. The reflecting surface is a plane. Now in all of these diagrams, ignore the colors. The colors that I put in here have nothing to do with the colors of light. They're just put in so that you can tell where each reflected ray is. The green ray goes like that, the blue ray goes like that. And they all come out in the same directions as if there were an arrow behind the mirror. And that's called the image. So the rays from the mirror are the same as if they came from the image. The object is an arrow, the image is an arrow. In this case, for a plane mirror, it's a virtual image. It's located behind the wall. There's really nothing there. There is no source of light back here. This is on the other side of the wall. So it's called a virtual image. Virtual in the sense that there are really no light rays coming from this arrow. It's just that the light rays that are coming from the mirror are coming in the same directions as if they did come from this arrow on the other side of the wall. The distances, well, because of the equal angles and the plane surface, the distance from the wall or from the mirror to the image, we call that dI for image, is equal to the distance from the mirror to the object. We call this D object. So DI is equal to DO. Image distance and object distance are equal. Also, there's no magnification. The image is just exactly the same size as the object. Just has a different location. It's farther away. If you're looking out here, from out here, you see the image as something sort of distant. You're closer to the object. All right, well, that introduces the idea of ray tracing. And now here is where things get interesting. Let's suppose instead of a plane mirror, we had a parabolic mirror. A parabolic mirror has the property, this is what I call a parabolic concave mirror. Concave because the source of light is on the inner part of the curvature of the parabola. So the object is on one side of the mirror. It's on the curved side of the mirror where you're on the interior of the curve. It's like you're in the cave. And again, we have a distance DO. That's the distance from the center of the mirror. And we're going to find there's an image out here. The image is at a distance DI. Now, this is a case of a parabolic mirror with a near image, a near object. So in other words, DO is less than the focal point, the focal length. So this distance is F for focal length. All right, now the way a parabolic mirror works is parallel rays go through the focal point. Parallel rays hitting the mirror are reflected and they pass through the focal point. So, for example, if this were a ray coming towards the mirror and reflecting, it would go through this focal point. And if this blue ray were a ray coming towards the center of the mirror, it would reflect at equal angles, and it would that's a bit different. It's not a parallel ray. Here's another parallel ray. A parallel ray goes through the focal point. This parallel ray goes through the focal point. This parallel ray goes through the focal point. Here, these rays are not parallel. Now, what I'm talking about in this picture are rays that are coming from the object, either because the object is luminous or more likely because the object is reflecting just daylight. So in that case, we have rays that go toward the mirror and then through the focal point. So here's a ray that's going toward the mirror. It's reflecting at equal angles, and it's a parallel ray, so the ray goes through the focal point. So the green ray is one ray we can trace. Here's another ray we can trace. It's a ray that goes from the tip of the arrow, reflects at equal angles from the mirror. Now the mirror is not parallel to the z-axis, so it's reflecting off parallel to the perpendicular of the mirror. So it's coming in with some angle, it's going out with the same angle, and in this case the angle is parallel. That ray which has an outgoing parallel ray, is the same as if the incoming ray were coming from the focal point. In other words, this is in the direction which at the tip of the arrow is away from the focal point. And it comes up and hits the mirror. By the law of reflection, it comes off parallel, because the nature of a parabolic mirror is parallel rays go through the focal point, or rays from the focal point come off parallel. And finally, we have this blue ray. Just ignore the color. Those are just to see the difference. They have nothing to do with the color of the light. The blue ray reflects from the center of the parabola. By the law of equal angles, these two angles would be equal. So it comes off down in this direction. So if you had a film or something over here and you were looking at the rays coming from the mirror, you'd see one coming down this way, and you'd see one coming from this way, and you'd see one way down here if the film is long enough. Those light rays have exactly the same directions as if they came from an image on the other side of the wall. So, for example, this red ray from the image, ignoring the mirror now, would just come straight across and hit the film. Or this green ray coming from the tip of the image and ignoring the mirror, it would just come straight down. It would go through the focal point and it would come onto the film. Or this blue ray would come straight down, pass on a straight line and down towards the film. So you see, the reflected rays have the same directions as if they came from an image over here in back of the wall. Of course, there is nothing behind the wall. There is no image. Well, there is an image, but it's not a real image. It's a virtual image. There's really nothing there. But the light that is coming from the mirror has the same directions as if there were an object on the other side of the wall, on the other side of the mirror. That's the image. Now you see from the picture, the image is magnified. And you also see from the picture, the distance from the mirror is larger than the distance of the object from the mirror. So it's farther away from the mirror than the object is. By analyzing the geometry of these rays, you can write the equation that determines the image distance and the magnification. 1 over dO plus 1 over di is equal to 1 over f. That's an equation you'll find in the textbook. And it's tricky because of the signs. dO will be positive. F will be positive. di in this case will be negative. When you have a negative image distance, that means it's a virtual image. So read about the meaning of this mirror equation in the book, but now in the screencast, let's just apply it. D0 we see is 2. And F is 4. So 1 over F is 1 over 4, minus 1 over 2 is minus 2 over 4. So 1 over di is minus 1 over 4. So di is 4. And that's this point here. 4. Only it comes out negative. What that means is it's on the virtual side of the mirror. Now what about the magnetization? Again, by analyzing the trigonometry of these various triangles, For example, let's look at this triangle and this triangle. They're congruent triangles. These angles are the same. So the tangent of this angle is HO divided by DO. The tangent of this angle is HI divided by DI. So the magnification is HI over H0. We actually use the equation magnification is minus DI over D0. Because remember, a negative image distance means that this length is minus DI. So DI is sort of the displacement, which can either be plus or minus. The distance or the length is the absolute value of the displacement. So it's always positive. Now in this diagram, the height of the object is 1.5. So what's the height of the image? Well, it's H0, that's 1.5, times minus DI, that's minus is plus 4. So 4 times 1.5 divided by DO, DO was 2. So that's 2 times 1.5, that's 3. And you see here, the image size from the diagram is indeed 3. So that's an example of ray tracing with a parabolic mirror. Now, a parabolic mirror is an idealization. Usually curved mirrors are made in a spherical shape. It's like a little section of a sphere. A section of a sphere is approximately the same as a section of a parabola, as long as the radius of the sphere is large. And what's the focal point for a spherical mirror with radius r? It's r over 2. So this focal point for a spherical mirror would be r over 2, where r is the radius of the sphere. Now, you would never have a complete sphere. You just have a little section of a sphere. So that's the radius of curvature of the sphere. All right, so let's go on to another example. So in this next example, we again have a parabolic mirror, which could be an approximation of a spherical mirror, but a far object. So the case we considered was a near object. The object was near the sphere. This will be a far object. The object is far away from the sphere, meaning farther away than the focal point. So here's the mirror. Here's the wall that it's mounted on. The focal length is this distance. So that's F. Parallel rays hit the mirror, reflect at equal angles, and go through the focal point. So I was wrong. That's not the focal point. Here's the focal point. This little dot here is the focal point. So this distance is the focal length. This distance is DI, the distance to the image. Here's going to be the image. And this distance is DO, the distance to the object. In other words, the distance from the object to the mirror. And as you see, we're considering a far object. DO is larger than F. And now let's analyze the rays. Well, in this green ray, just ignore the colors, but the one which is colored green, a parallel ray hits the mirror and goes through the focal point. So it's going off in this direction. And now let's consider the blue ray. Well, the blue ray is hitting the center of the mirror. By the law of equal angles, these two angles have to be equal. So it will come off in this direction. And then finally we have the red ray, which goes through the focal point. By the law of equal angles, it comes out parallel. Because parallel rays go through the focal point. So a parallel ray coming in and out goes through the focal point. Or a parallel ray coming in through the focal point goes out along a parallel ray. So if you put your film down here, you'll see rays of light coming in these directions. And if we trace those back, they're exactly the same as the rays of light from this image of the object. There's no object here. I mean, there's no thing here. But all of the light comes from this place, because all the light was reflected through that thing. So as far as the lens is, as far as the film is concerned, you could just as well say the light came from the thing right here. That's the image. This is called a real image because there really is light at this point. It's light that came from the mirror and went through that point. Came from the mirror in all different places along the mirror. So from all different points along the mirror, there's light going through that point. So there really is light at this point. So this is what's called a real image. There's a real image located in front of the mirror. So in the case of mirrors, virtual images are on the opposite side of the mirror. Real images are on the same side of the mirror. It's at a distance di. And you see from the diagram, it's inverted. That is to say, if the object is upward, the image is downward. And it's reduced in size. Unlike the other case, where the image was larger, in this case, the image is smaller. Larger or smaller than the object. Again, we can use this same mirror equation, which you find in the textbook. 1 over dO plus 1 over di is 1 over f. Now in this case, f looks like 3. Let's see, is that right? Looks like f is 2, not 3. So I must have this wrong. I guess f is 2. dO is 5. 2, 4, 5. Now, in applying the mirror equation, dO and f are always positive. So I have 1 over 5 plus 1 over di is 1 over f. So what's di? Well, let's see. We have 1 over 2, move this to the other side of the equation, minus 1 over 5. So that's 1/2 minus 1 over 5 is 3 over 10, 0.3, 0.33, 333, no, 1 over 3, 0.5 minus 0.2 is 0.3. So that says di is 1 over 0.3, which is 3.33. So this is wrong. It's 3.33. And does that agree with the graph? Does that agree with the figure? It's here. So here's -4, here's -2, here's -3, here's a little bit more than -3. It's -3.33. So the mirror equation agrees with the ray tracing diagram. What about the magnification? Magnification is the height of the image divided by the height of the object, and we use the formula minus di over d0 by looking at triangles in this diagram. Let's see, which triangle would it be? This triangle and this triangle. Those two triangles are congruent. They have the same angle here. So HI divided by DI is equal to HO divided by DO. Well, HI over HI is DI over DO. Now, we could include the sign. So if you include the sign in the formula for the magnification, HI over DI is minus DI over D0. H0 is again 1.5, so that's 1.5. DI over D0 was 3.33 divided by 5. So you would have 1.5 divided by 5 multiplied by DI, which was 3.33, which is 10 divided by 3. So this will be 15 divided by 5 is 3 divided by 3. So this will be 1. So I got this wrong. This will be 1. Or actually, if I include this minus sign here, this will be minus 1. So HI is actually the displacement. It's downward. You see the arrow is pointing downward. So when you have an inverted image, the sign of the displacement is negative. The length of the image is the absolute value of the sign. So that would be 1. And let's see if the formula agrees here. Yeah, this length is indeed 1, because this length is 1.5. So you see how ray tracing shows you what's happening. And then you have a big trigonometry problem or a big geometry problem to calculate things like the image distance and the image height. Well, you can get those from these equations from the book, but you have to be careful about the signs. For a real image, the sign of the displacement is positive. You see, it's in the same direction. It's on the positive side. The positive side is the side of the object. Well, the image is also positive. But the height or the vertical displacement will be negative. So, you have the ray tracing diagram to help you understand what's happening, and you have the equations to calculate numbers. You could calculate these numbers by just analyzing the triangles in this diagram. But if you just want to apply the formula, you have to be sure you understand the signs. All right, well, I think that's enough about mirrors. I mean, obviously, there are other problems. For example, you could have an object over here. That would be called a convex mirror. This is a parabolic concave mirror. If I had the object over here, that would be a convex mirror. And the ray tracing would be very different. And there'll be a LON-kappa problem like that. But again, I think it's probably worked out in the textbook. Again, you can use this formula if you understand the signs. But I want to go on now to lenses. Okay, lenses. A lens is a piece of glass in the shape of two hemispheres glued together. In the most general case, I could have a different radius of curvature on one side of the lens and a different value for the radius of curvature on the other side of the lens. But for the simplest case, they would have the same radius of curvature on both sides of the lens. So it would be lens shaped. It would be shaped like this. Now, unlike a mirror which reflects, a lens transmits light. So we'll start with a convex lens with a far object. What is meant by a convex lens? Well, if you draw the line through the center of the lens, and now you consider rays parallel to that line, they will be deflected by refraction into a point down on the axis. That point is called the focal point. So this is the focal point. And for an ideal convex lens, parallel lines all go through the same focal point. So the light comes in this direction. It goes through the glass. It's refracted on both sides, and it ends up going off in this direction, the direction connecting to the focal point. And of course, a ray going right through the center of the lens, parallel through the center of the lens, will just come off in the same direction as the axis. So here's the axis of the lens. All right, now let's suppose we have an object, and we'll draw it again as an arrow, emitting light. See if we can blow this up a little bit. Emitting light. Ignore the colors of these light rays. That's just so that you can tell them apart, but there's nothing. This object is yellow. It'll emit yellow rays. But if I put all these rays in yellow, I couldn't tell them apart very well. This parallel ray goes through the focal point. So here's the focal point. There's no wall. So the light just goes through the lens and down through the focal point, comes out in this direction. Here's a ray which goes through the center of the lens. Well, through the center of the lens, after the two refractions, it'll be coming out in the same direction. So this is the direction of the ray that went through the center of the lens. You know, this angle and this angle will be equal. So it's just going straight through. Whereas this angle, in this case, the angles are not equal because of the refraction. And then finally, we have this blue ray. It's the ray that goes through the focal point. It comes out parallel because parallel rays go through the focal point. So if I had a ray coming in from the right, parallel to the axis, it would go through the focal point. Or if I just reverse the direction, the ray from the tip of the arrow through the focal point to the lens comes out parallel. So then if you observe these on a film or something, you see I have rays coming as if they came from an image right here. They're all coming in the same direction as if they were emitted at this point. So that's the image. The light rays that are coming from the lens are coming in the same direction as if they came from an image here. And so as far as the film is concerned, it can't tell the difference. It just says, okay, there's something there. In fact, there is nothing there. But the light is coming from that point. So that's another example of a real image. So what we have here is a case where there's a convex lens with a far object. You see, the object is far away from the lens, far compared to the focal point, the focal length. This is the focal length. It's the distance from the focal point to the lens. This is also the focal length. The two focal points are on opposite sides of the lens. So I have a focal point here with length f. I have a focal point here with length f. This is DO, the distance from the lens to the object. And this is DI. Now you see this is a far object because DO is quite a bit larger than F. You see the image, it's on the opposite side of the lens. That's a real image. That's called a real image because there really is light at that point. All of these rays are going through that point on the tip of the arrow. Now, it's inverted. So if the object points upwards, the image points downwards. So it's upside down. And you also see from the diagram, it's reduced in size. So let's calculate the distance to the image, that's DI. And again, we have an equation, the lens equation. 1 over F is 1 over D0 plus 1 over DI. Now F, you see in this problem, is 2. DO is 5. So 1 over DI is 1 over F, that's 1 over 2, minus 1 over DO, that's 1 over 5. So that's 0.3, that's DI. 1 over DI is 0.3. So DI is 3.33. If we look back at the diagram here, yes, the image distance it's between 2 and 4. It's a little bit closer to 4. It's 3.33. So that agrees with the image tracing. And now what about the magnification? We define magnification as H0 over HO, which is a given by minus DI over D0. You can figure that out by looking at the various triangles here. Have to be careful about the signs. So M is minus 3.33 over 5, so that's minus 0.667. HI, that's 2/3. HI will be 2/3 of the height. The height here is 1.5, so 2/3 of 1.5 is again 1, but it comes out negative. That's because the displacement is downward. It's inverted. So a negative displacement length corresponds to a downward or a inverted image. So there's one example of the analysis of a lens. There are 3 other examples. I'm only going to do one other example in the screencast. We'll go on to that in a minute. We analyzed a concave lens with we analyzed before a convex lens with a far object. Now, there are 3 other cases. A convex lens with a near object, a concave lens with a far object, or a concave lens with a near object. Well, let's work out one of these 3 cases. Let's consider a concave lens with a far object. So here's the object. Here's the lens. Now, a concave lens is a diverging lens. So parallel rays diverge from the focal point. They don't converge toward the focal point. That would be a converging lens, which would be a convex-shaped lens. They diverge from the focal point. So here's a parallel ray. By refraction, as it goes through the lens, it comes off in the direction toward the focal point. Let's look at the green ray. That's a simple one. The green ray goes through the center of the lens. Well, it will come off with the same angle that it comes in with because the refractions are equal but opposite. So this green ray just comes through the center of the lens. Those are the 2 that are easy to analyze. One that comes parallel to the lens and then diverges from the focal point. And then one that just goes through the center of the lens. And you can see they cross at this point. Well, no, they don't cross. But if I trace this ray back to the other side of the lens, that traced line crosses the green ray at this point. So the image will be here. Now we could try to get one more ray. We could consider a parallel ray. Let's suppose we have a parallel ray coming in from this direction. Well, it will then diverge from this focal point. So it'll come up in this direction, diverging from this focal point. And if it's at exactly the right height, it'll go through the tip of the object. So you would have, again, 3 rays from the tip of the object, which go to the lens and come off in 3 different directions, diverging. And if you trace those directions back to the positive side of the lens, to the object side of the lens, they would all cross at this point. So this distance is D image. The distance from the lens to the image. The point where all the diverging rays trace back to. This, of course, is D0, or D, I shouldn't say 0, DO. It's the object distance. And here is the focal length. The focal length is this distance. Well, you see from the numbers, the focal length is 2. So now, let's calculate DI and the displacement, HI, the displacement in the image of the tip of the object. So, well, first of all, from the ray tracing, we find out that the image is a virtual image. There's really nothing here. And there isn't any light here either. There isn't any light coming from that point. You know, this red ray doesn't really, I mean, this is not a ray of light. This is just tracing back this ray of light. And similarly, the blue ray. So this is not a real image, it's a virtual image. It's upright. It's upright. It points in the same direction as the object. And you can see it's reduced in size. So now let's calculate di and hi. Well, we have the lens equation. 1 over f is 1 over do plus 1 over di. F is 2. But for a diverging lens, we say that f is minus 2. So you have to know the signs. You have to look up in the book the signs that you assign to these various quantities. F here is really the displacement from the lens to the image point. It's negative. So F is minus 2. D0 is 4. This is the positive side of the lens, so D0 is 4. DI is 1 over minus 2. So that's minus 0.5. 1 over minus 2. Minus 1 over D0. So that's minus 0.25. 1 over 4. That's minus 3/4. So 1 over di is minus 0.75. Minus 3 over 4. So di is 4 over 3. So it's 1.33. But it's negative. So it's negative 1.33. Negative meaning that it's on the same side of the lens as the object. So the signs are a little tricky, and you have to kind of look up in the book. I think in the book there's a little table which shows you the signs for different cases. When in doubt, you can always go back to the analyzing the triangles in the ray tracing diagram. Now what about HI? Well, again, if you look at these various triangles, for example, look at the green triangle. This side, they are congruent triangles because this angle's the same. So the tangent of that angle is HO divided by DO. Or the tangent of that angle is HI divided by DI. So HO divided by DO is HI divided by DI. Or HI over H0, that's the magnification, is minus DI over D0. And you have to be a little careful about the signs. But DI we know is 1.33, so minus DI is actually plus 1.33. H0 is, in this problem, H0 is no, I'm looking at DI over D0. DI is minus 1.33, so the minus sign cancels the minus sign. Now I want D0. D0 is 4. So I have here 1.33 over 4. That's 4/3 divided by 4. That's 1/3. The signs have canceled. So it's 0.333, 1/3. So the image is 1/3 as large as the object. The object size is 1.5. A third of that is 0.5. So HI is 0.5. In this case, I get a positive displacement because it's upright. So you'll get some practice on the law and Kepler problems analyzing these mirrors and lenses. And I would say the first thing you should do is look up the various formulas that apply depending on whether you have converging lenses or diverging lenses, concave mirrors or convex mirrors, far objects or near objects. There are about 8 different combinations. Well, make a little table so that you get all the signs right.